explain what this consortium is about to a degree. Does that advance it? Yeah. So we are based on, or the reason we are doing this research is because of exploration in Australia, which is difficult for many reasons, and I'll explain why. So first of all, if you look at the size of Australia on that scale bar, you know, Australia is big. It's about 4,000 kilometers across, 4,000 kilometers. So that's a long time. I can tell you it's 5 hours on an aeroplane. So it's a big area. And what this map also shows, besides the size, is in these colored areas are areas where there's outcrop or close to surface exposure of rocks. So areas in Western Australia, in the northern area, the centre. But you see there's not many areas of Australia. Only 30% or so of Australia has outcrop. So this is a big significant problem for exploration in Australia. But now also what you see on this map is that where there are not coloured areas, the geophysics clearly shows, of course, that the outcrop can be seen under many areas of cover, extending under cover. Now that cover varies from, you know, a few meters thick to 1,000 meters thick or more. There's some very thick basin cover, but clearly the geology, as you would expect, extends from the outcrop areas to the areas under cover. And if you look then at where the drilling has been undertaken across the last, 50 or so years in Australia, these dots each represent a drill hole. They've been coloured by nearest neighbour, so the closer ones basically are in the redder colours. But on open file, so it's easily identified, there's probably 700,000 holes on open file. But if you look where the drilling is, of course, the drilling is where the outcrop is, because that's where you start drilling and the first things you discover. And the more you discover, the more you drill and explore in those areas. So logically, much of the drilling is in exposed areas with very few holes in some of the deeper cover areas, very poorly understood. And if you add then together, of course, the outcrop where people started exploring and then logically did drilling, and if you then add to the mineral deposits, well, you know, it's such a clear picture that all the known mines in Australia, and these are mines coloured by size of the mining area and the commodity, are restricted so much to those areas where there's outcrop and, of course, where the drilling's been undertaken. These are the iron ore mines in the northern part of Western Australia. There's gold and nickel primarily in this area, Olympic Dam and copper, and then gold and a lot of coal, of course, in Queensland. But you can clearly see that where there's outcrop, people have worked. Where they've worked, they've drilled. And where they've drilled, they've found deposits. But, you know, the big question is, well, how do we explore more efficiently, for example, in areas like this, where you know the geology extends undercover, there just has to be something there, but it has not been discovered yet. So that's the whole premise of doing further research and understanding how better to explore in areas that are covered to discover surely as many mines as there are known in the exposed areas, in the areas that are hidden under cover. So I think that's quite a compelling reason to carry on exploring in Australia. There's lots of area left and lots of space to explore. But of course, undercover requires technology. You can't walk around anymore. The days of just prospecting are long gone. The days of cheap geophysical are long gone. So it requires a cooperative approach to tackle this. So in our case, this concept of a cooperative research centre, a CRC, is something the federal government funds to have research that is industry-led. So industry must suggest what you want to do, and in this case, find and more efficiently explore. And the federal government puts in some money, industry matches the cash, they put in the research organizations put in people, researchers, and they also put in in-kind contributions, equipment, technology, etc. So basically, the government gives some seed funding or stretches the funding of industry along with research organizations and companies that can actually commercialize any discoveries over time. And this cooperative research idea in Australia has been going for 30 years now, and it covers many fields of research. So there's research into sheep and into space and data and fish and all sorts of things. So it's of course not just minerals, but there are many types of research centers. But in our case, we are for mineral exploration with a 10-year life we've been given. And so far we've been so that 10 years is divided into three-year phases. And we've just finished our first 3-year phase, and we're into the second phase of 3 years with different projects, which I'll touch on now. So as I said, total cash over 10 years, quite a significant amount of cash, non-staff in kind, so equipment. We've got a drill rig from a supplier, we've got data, and about 100 researchers at the moment scattered across these projects, with actually up to now 35, even 36 postgrad students, with, of course, industry-led, understanding everything we explore has got to be safe, environmentally friendly, producing data to better inform decisions, for example, where to explore next. So that's the concept of cooperative research and how we're undertaking it in that way. So who are all these companies? Well, there's a range of companies. There's the big companies, BHP, Anglo American, South 32, so mining companies, of course, doing exploration. And then there's the what we call METS companies, the mining, engineering, technology, and service companies. Epiroc, of course, you may know as Atlas Copco in the past. There's a Chilean drilling company, Seismics, there's Index, there's drilling companies, Sandvik, so numerous supply companies as well as the mining companies. And then the geological surveys. So we've also then convinced the geological surveys that to stimulate exploration, the state government bodies, the surveys, must also help to open up areas for further exploration, and opening up areas for further exploration also requires better techniques. So that's the first page of that, and then numerous other universities. So universities here in Perth, where I am located, Adelaide, Australian National University in Canberra, and of course our national research body with other contributions here, and then various smaller organizations or affiliates who take part in specific projects, but not numerous projects, of course, and Datacode having been with us for nearly four years now from the start, which is excellent to see that. So yes, a range of companies, big and small, come together to share ideas and understand better how to explore and what services can be offered with that exploration. So that's the concept of the companies and the people. So what do we do actually? Well, I'll go through the 3 areas of research, starting on the left with drilling technologies. So the technologies themselves generating samples. From there, I'll go into the data generated and then putting it all together in what we call the National Drilling Initiative. So on drilling technologies, where by far the most money is spent, and the first project is what we call drilling optimization and automation. Now, as you'll be aware, you know, both diamond drilling and reverse circulation drilling, or RC drilling as we call it, those are the 2 main methods of exploration, and vary from shallow drilling, 50 meters to 2,000 meter holes with diamond drilling. But there's a lot of drilling, you know, just in iron ore alone, there must be about 2 million meters a year drilled for drilling out ahead of that big iron ore production. So, you know, total drilling 4 or 5 million meters easily in Australia. So a lot of drilling gets undertaken. So any small incremental improvement in costs are valuable. And that's why some of the companies have come to us to say, how are we going to increase drilling productivity? And one method looking at in 3 areas of drilling. So reverse circulation drilling, used extensively here in Australia, especially in covered areas, down to commonly 200 meters or so. Diamond drilling for either 2 purposes, one to drill deeper deeper than RC drilling can drill, and of course for core recovery. And thirdly, automation of drilling fluids. So fluids for both RC and diamond drilling, and how you better automate them. And basically, one of the ways in the first 3 years of doing this research is by instrumenting up rigs. And on the left here, we just have a diagram of from an RC rig, which we instrumented up, but recording huge amounts of data, 20,000 hertz of data, 20,000 readings a second, so that we can better understand hammer strike, pressure, for example, and speed of bit and advance. So a lot of work into very technical aspects of drilling, understanding the drilling itself, and then ultimately how we can automate some of those decisions and take the decision away from the driller necessarily. And the same as for diamond drilling, weight on bit versus penetration. The more you push on a hole, that's good, but then you run out of fluid and cooling, for example, you can burn the bit. So there's a significant sweet spot in diamond drilling on rate of penetration and a whole lot of other factors, weight on bit, and of course deviation. And so that's for example then taken onto research of drill bits. So, what the best forms of drill bits, normal with face fluid flows, face discharges, all sorts of different testing that we actually can do in one of our facilities on just drill bits themselves. Because what is amazing, the amount of money spent on exploration in Australia and globally, but there's very little technical work on drill bits that you can verify the exact quality and type and rock types that a drill bit is suitable for. Most people just use them, and if they work, they work. But it's not a very scientific way of doing it. So we see opportunities for improvement, for example, in drill bits, and eventually all of these add to algorithm-based drilling automation. So understanding the data, building algorithms, and utilizing that to improve your drilling itself. With recording systems and algorithms ultimately. So various ways of drilling. And that is what you would call conventional drilling, both reverse circulation and diamond, by far most common. But we have a second project looking at a totally different way of drilling, and that's with a coil tube rig. Now, this is a rig you may never have seen before in mineral drilling, because there is no one in mineral drilling that drills with a coil tube rig. And I'll show you a few more pictures of it. But basically, coil tube, that there has 500 meters of coil on there, of steel tube. It's about NQ size diameter, 70 mil, for example, a hole approximately. And this rig, this is just the pure rig on its own, weighs about 16 tons, so not very big. Has a spool that then straightens it out and can advance using fluid-driven hammer or downhole motors. So it's all a water-driven, fluid-driven system. And basically, the quest is to utilize this coil tube drilling for mineral exploration to get a sample that's equivalent to diamond drilling, and also recover core at the end of the hole, because normally this produces chips, with also being able to position and steer and sense the hole, as well as get to 1,000 meters depth with the second version of that. So the coil tube is a very different way of doing things. It's suitable in Australia because of a lot of that cover rocks. It can go through cover very quickly. And we now have a coil tube rig we've been drilling with over the last 6 months. We've drilled about 5,000 meters so far, with what is a totally different drilling technique. So we're still learning ourselves and exploring it. But this is an exciting way of trying to do drilling very differently. It will never replace all diamond or RC drilling, but it's certainly got its niche, which we're working on for that drill rig to work. So I'll show you a few more images. Basically, with the mast down, you can see it's not a very big unit next to a vehicle there and a person. As I said, about 16 tons. This one's on tracks, so it can be tracked around. Quite compact drill rig, and that's you can see the coil on there. We also have actually a 1,000-meter version. This is a prototype version. We haven't tested in the field yet, but that's 1,000 meters of coil on there. And you can imagine going into and out of a hole. This is, of course, at an angle, but it would normally drill from 60 degrees to vertical. You can go into a hole, a 500-meter hole, in about 20 minutes, put all the coil in a hole. And if anyone is familiar with a normal drill rig, diamond or RC, unscrewing 3 or 6 meter rods, it's time consuming. It's often dangerous because if many people have heard of stories or seen what happens when you drop a heavy drill rod on someone's toe, and you know, there's safety concerns. So this, you don't have drill rods to worry about, although it does have a head, a rotary head also, that you can put collar pipe in. So you can put a 30 or 50 meter collar through unconsolidated sediments, for example, and then carry on with this. But it's not just a drill rig that's important, because you're drilling with fluids, driving a downhole motor, open hole drilling and returning a sample, that the fluid processing is very important. What you do to capture the sample, because you can use and utilize a lot of fluid if you're losing fluids. So the second part of the drill rig is this hydraulic processing system. Basically, that's just our processing truck. And on this, we've put this together over the last year and a half. It can contain fluids. It's got its own generator. There's a sample shaker here, so sampling off these 3 points at the back here. It has a horizontal centrifuge. So the centrifuge is for taking fines out all the way down to 200 ppm. It has its own, of course, power bank, and then even remote fluid dosing applications. Because the important thing also about drilling without casing and open hole is you have to control the fluids and the hole itself for stability. So we've been doing a lot of work to ensure the drilling muds we use, of which we hold some patents on these muds, hold the hole open when they stop flowing, but can flow at high speed and very low viscosity, when they're flowing fast. So we've got a bunch of drilling fluids we use. Flow fast, can go through a hammer, but can stabilize the hole and set like treacle when they stop in a hole. So coupled this, the hydraulic processing system, coupled with the drill rig that you've seen, is how we're drilling at the moment. And I'll show you some images of that and some of the results. So a totally different way of drilling. And then we're generating data, of course. So through 4 of the projects we look at are different ways of generating data, not just from those drill rigs we've been talking about, but we're looking at 4 different projects associated with generating data. And the first one is real-time downhole assay. So you may be familiar with LIBS, or laser-induced breakdown spectroscopy, which is in fact what has been sent to Mars on the Mars rover. So you shoot a laser at a rock. It, of course, emits a puff of dirt, you may say, and the spectra can be read. So that's a concept. It's a simple concept. But having said that, it may be simple on Mars because there's no atmosphere. But what we're trying to do is use this LIBS, or laser-induced spectroscopy, and put it down a borehole. Now, that's quite a challenge to put it down a borehole because the borehole is narrow. We're looking at a 80 mil borehole, and basically we're trying to fire a laser out of onto the side wall of a borehole, measure the spectra, and then interpret it in real time. Now, that's quite a challenge. We've been going 3 years. We've built a setup in the lab. We have a laser, of course, a LIBS laser, which is working on moving surfaces that are dirty, surfaces that are wet, and narrow. So the next challenge in this 3-year phase is to apply it in real life situation. But it's a good thing to try, because really you could get 1,000 readings every meter down a hole ultimately. So you would have a continuous analysis down a hole is what we are aiming for ultimately. This is probably early phase research, because there's a very good chance it may fail, but there's only one way to find out, and that's to build it and explore and do it. But this project, for example, and the next 2 you'll see on geophysics, the reason why you can do those is because with the coil tube rig, the rods are not spinning, of course. only the motor at the end of the hole is spinning. So if your rods aren't spinning, you can have power and communications down the middle of your tube, which we have got. So we've got copper cable for power. We have fiber optic cable for communications. So you can build tools like an assay tool, geophysical tool, and have them real time at the bottom of your coil ultimately, because you have power and comms at the bottom of your coil and your rods aren't spinning. So that's quite a thing, coupling innovative ways of geophysics with the ability to have power and comms to the head. So that's our downhole assay. Then, of course, we have two other ones, as I said, the geophysics themselves. We have already a natural gamma sensor, and we're developing an EM sensor, ideally suited to coil tube drilling. You have power and comms, you can put it down the hole so that while you're drilling, ultimately you can steer towards, for example, an EM anomaly and measure natural gamma as you go, along with a gyro, of course, for positioning. Mm-hmm. And the second part of geophysics is not necessarily just the sensing, but doing seismics. So seismic in the drilling workflow. So what we're doing is utilizing fiber optics, which we mentioned before, to basically reduce the seismic costs of surveys. And this little buggy on a dry lake bed is laying out fiber optic cable behind it in just a narrow trench, and below it is just the pattern of laid out in 3 days, laid out about 30 kilometers of fiber optic buried beneath the surface, just by a few centimeters, and then single shot trigger source to measure basically low cost seismic surveys instead of the traditional big vibroseis trucks that you may have been familiar with. I think I've got a picture of them a little later. So it's low cost seismic on the surface, as well as putting these fiber optic cables down boreholes. So for both active seismics and passive seismics, where you can leave a fiber optic down a hole and just use natural sources, for example, blasting or excavation in a nearby mine and picking it up because it's a very sensitive receiver. So we've done a lot of work on the best type of fiber optics for configurations down a hole, spiral, for example, helical, and how to put them in holes and recover them too. So that's the seismic aspect of exploration, and a separate project. And then lastly, a project that actually Datacode has been involved with also, which is 3D automated modeling. Because the challenge faced by geologists all over the world is to build a geological model with drill data can be a task that takes weeks, months. In fact, the big companies for a big data set can take a month or in fact 2 months to build a decent geological model, which then of course still needs to be converted into a resource model. So this is putting diverse geological data together to generate probabilistic 3D models, which of course are not influenced by the spacing of your drilling, but taking into account uncertainty and plausibility filters. And the aim is to reduce it from weeks and months down to a week, in fact, in a matter of hours, pushing a button to generate a 3D automated model. So a lot of course, the data has got to be good going in, but interesting is that this is an open source project. So the results are available to be seen. If you look on the Minex website, some of the end results are already there, but basically putting it out for people to make better geological models. So those first 6 pure research projects that we're undertaking. And then we're applying much of that in the National Drilling Initiative. So across Australia, different companies, different organizations, different geological surveys have now used different parts of our research and trying to understand mineral systems, the regolith, so basically the regolith interface of those systems, and then the geology and properties from drill holes, and delivering that data to parts of the country to stimulate further exploration. And as I said at the beginning, to try and better understand areas undercover. So that national drilling initiative, I'll give you an example of the type of what we're doing. So you can see parts of Australia has got not many people and not many trees and nothing much at all. In fact, these are seismic trucks, so they're big trucks up in the Northern Territory, and yeah, there's a lot of nothing for a long way. And of course, as you can imagine, doing geology in these areas is not easy unless you're either doing seismics or doing drilling. So the challenge is, how do these areas get at least some stimulation that companies want to go and explore further to have discovery? And these are these scientific programs to give general geological knowledge so that companies then go and explore later and better. So in this case, following a previous seismic line, we then went out and undertook a drilling program. Here's one part of that drilling program, and we called it a scientific drilling program. So we weren't exploring for mineralization. We weren't trying to find a mine. Many companies have that as their job. We were trying to open up further areas. And here's an example of a diamond rig drilling these holes. It was just changing over the rods. Those were about 600-meter holes. That one was in that case. And there's just a little graph of the 10 holes we drilled in this area, and I'll show you the effect of drilling holes in an area where no one would normally drill, because there's no reason to drill there unless you can. There's no reason to drill there unless you want to try and stimulate exploration. So we drilled 10 holes. That's the depth on the left, about 350-meter holes, 400. One was down to 750 meters, diamond drilling. The collar on each case was with reverse circulation or mud rotary. So you can see most of these at about 150-meter collar, cased off, and then diamond drilling across a fairly wide area. And those 10 holes, utilizing some of our technology we've developed already, followed by geophysics, were drilled and logged. And this is the type of data that was put out on our portal, so readily available for the public. So, for example, a completion report, what's the geology, stratigraphic log, lithologies, groupings of lithologies, petrophysics as well. We ran downhole petrophysics. We did XRF, portable XRF on the rig, and then, of course, assays, laboratory assays after that, photography, mineralize, and the public can see the core. So what happens if you spend money on a program that a company would not normally do and put the data out there? Well, in our case, first of all, some of the holes were actually more successful than we thought. There was mineralization, there was iron ore, copper, gold style alteration, and some sulfide even in one of the holes. So the aim was not to do to explore just for minerals. It was to open up an area, although there were some areas that were opened up even more than we thought. And there's some sulfide in one of the cores. So what happened that now Minex, utilizing its technology and utilizing these areas where there had been no drilling, then did this drilling. And I'll show you this area. So this is in the Northern Territory, northern part of Australia. It's quite remote. There's very few people who live in those areas. There's two main roads that intersect, and in this area here, and you can see the scale, so that's about 100 by 50 kilometers, a little bit more than that, 130 by 70 kilometers. We drilled 10 holes in this area scattered around. Previously, there, I think, had been one hole in this whole area, and with no knowledge, as you can see from those pictures, there's no outcrop. These were the existing tenements. So in 2019, 2018, 4 companies held exploration tenements for some reason in those areas. That was, so what happens then, we did this drilling and released the data. And by 2019, the people knew we were going to do drilling, and you can see some companies started picking up some more tenements in that area. By 2020, more companies had realized, gee, drilling's going on and this data is looking interesting. And by the end of 2021, this area, which is even much bigger than our area we drilled, so an area of that must be 250 by 200 kilometers, has now got 36 companies who've pegged leases in that area and are actively exploring. So, that's the effect of stimulating exploration by drilling holes in an area just to understand the geology. And the understanding was, well, there could be iron ore, copper, gold, mainly copper mineralization, but gold, and there's some lithium interest. Of course, everyone's interested in lithium at the moment, but the result of spending that seed money is this staking rush, really. It's a prospecting rush, 36 companies, and a lot of money being spent now. Of course, we don't know if it's going to generate a mine or big discovery, but that's the only way for countries and companies to open up areas, is to stimulate exploration in this way. This was in the Northern Territory, and as we speak, we're drilling in South Australia as well. That's just an image. Intense weathering. We've discovered some quite good unknown rocks. There's a diamond rig drilling in this area here. These are wheat fields at the end of the harvest season with a conventional rig, and we're using our coil tube rig at the moment as well. So that's the rig you saw earlier in action. When it spins, it's actually quite boring. It's quite a slow rotation of the coil. Straightens the rod down the hole. Next to it is the hydraulic truck I talked about for processing samples, and simple as that. Many people ask why in this picture is there hay bales here. Well, there were some farms over here, and they could hear the noise of the rig, and we did the right thing and put hay bales up as a as a sound barrier. And of course, a nice photo taken at sunset when everything was nice and green. A few months later, it was very brown when the rain finished. But so that's us again in the second area, hoping to do again what we did in the Northern Territory and open up areas of the country utilizing new technology to drill cheaper and better, so that companies come in afterwards and do even more exploration. And then lastly, I'll just touch on the market in general in Australia, which I don't know how similar it is to the Indian market, but what this shows over the last 18 years, from 2003 to 2021, both on the left-hand side, the meters drilled. So in red, how many meters drilled every quarter. So that's, over 1 million meters drilled in a quarter. That's 4 million in a year. And peaking 2008, as Sushil will recall, and then it fell off a cliff, and then peaking again 2011, 12, and then flat for a number of years, and of course way up at the moment. And that's the meters drilled. Now, expenditure on exploration is fairly similar. Now, you may argue, well, which one drives the other one? But expenditure on exploration, this is in Australian dollars, so 0.75 of that is US dollars, but that's close to 800 million US dollars a quarter, every 3 months, on exploration in Australia at the moment. So a lot of money is being spent on exploration. More money is actually being, more drilling, drilling and exploration are mirroring each other, but very busy at the moment. So there's a lot of global money available for this sort of thing. And of course, there have been many, we call them IPOs, initial public offerings, so many companies listing on the stock exchange and raising further money. Now, the problem, though, in Australia, with a lot of money in exploration, a lot of meters being drilled, is there's not enough people to do the work. Many drilling companies have drill rigs standing idle because they just cannot get the people. People can't move interstate, or previously they couldn't do that with COVID restrictions or didn't want to move. So there's quite a big shortage of people. So the market's oversupplied with cash and undersupplied with ability to do it. And then, of course, because there is a lot of drilling, the laboratories they have 2 or 3 month waiting times on samples for both, because a lot of volume's coming in and there's just not enough people to process it. So it's quite an issue, as well as environmental, social and governance issues, which in other words, you're all familiar with Rio Tinto and the Juukan Gorge when that cave was blown up. That's affected everyone because people are cautious now. Of course, there's even more heritage surveys, more archaeological surveys, and more restrictions on ground. So the market in Australia is very hot. People want to do exploration. They want better ways of doing it. They're funding projects with us, but there are also constraints on the market. And then lastly, I'll just finish with a picture. So we are a research organization scattered actually with a very small head office, but scattered across many, many different research universities with people in many places coming together, being driven by what industry wants and applying that. And you can see from those Northern Territory examples that it's very effective if you use some seed money and some good techniques in an area where many, many people then can go and explore further.